In our next example, we are going to back up or illustrate another set of formulas that we talked about earlier in the section, which is the idea that if you have two independent events, that the probability of this, there was a formula that said the probability of A should be equal to the probability of A given B, and also the probability of B should be equal to the probability of B given A. So in this experiment, we are going to be rolling 2 fair dice. One is white and one is black. We are going to have the event A, the white die comes up a 2, 3, or 4, and event B, the black die comes up greater than 4. It says it's intuitively obvious that what happens on the white die does not affect the result on the black die and vice versa. So we expect that whatever happens on B will not change the likelihood that A occurs. So again, showing this will basically show that those two formulas are indeed true if your events are independent, which these definitely are in this case. These are independent. So let's show that these two statements are true in an independent situation. Okay, so what I've got is an illustration here of events A and B. So this is event A out to the side, which is showing basically there are 36 different things that could happen when you roll 2 die. Like you could get a 1-1, a 1-2, a 1-3, a 1-4, and so on and so forth. So this has got all of the different options. So everything in this one box right here would show the white die landing on a 2, 3, or 4, and everything in this kind of vertical box would show event B, the black die, coming up greater than 4. So let's see, what's the probability of A? By definition, that is the number of sample points in A over the number of sample points in the entire sample space. So in how many ways could A occur? If you count up all of the X's in this box that represents event A, there are 18 of them. So there are 18 different results for your white die landing on a 2, 3, or 4 out of 36 total possible outcomes, because again, we're rolling 2 die, so there are 6 times 6 or 36 different outcomes. And we can reduce that down to a half. That makes sense because 2, 3, and 4 are half of the options out of 1 through 6. So if we're just talking about one of the die, that would be a half. Okay, the probability of B then again has a denominator of 36. But how many different ways can the black die land on just something greater than 4? So land on a 5 or a 6. There are 12 ways that can happen, which reduces to a third. Okay, let's look at the probability of A given B. By definition, that is the number of elements in their intersection over the number of elements in B. Okay, so we know how many are in their intersection. Notice that there is this area right here of overlap. That's the intersection. So there are 6 ways that could happen. Out of how many, again, elements are in B? We already said that there are 12. And 6 out of 12 reduces to a half. And then let's reverse it. What's the probability of B given A? Well, there are still 6 elements in the intersection, but this time we want to use the number of elements in A. So in that A box, there were 18. 6 out of 18 reduces to a third. So what we've done is just sort of visually, and by doing a particular example, shown that if in fact your events are independent, which rolling 2 die, they don't affect each other, that's independent, then you can see that the probability of A is still equal to the probability of A given B. So whatever happened on B, we just showed that it does not affect at all what happens on A. And the same thing, the probability of B is equal to the probability of B given A, because being given the information of what happened on the white die doesn't affect what I think is going to happen on the black die. So that just backs up and again confirms these definitions that we were given earlier in the notes. Okay, let's see. A pair of fair dice is cast. Let E denote the event that the number landing up on the first die is a 3, and let F denote the event that the sum of the numbers landing up is 6. Determine whether E and F are independent or dependent. Okay, so in this case, we don't know whether they're independent or not. So let's check to see if the formula checks out or it doesn't. Okay, so the event E is the first die has to come up a 3. Okay, so let's see. That could be a 3-1, a 3-2, a 3-3, a 3-4, a 3-5, or a 3-6. That would be all of the different ways I could roll 2 die, with the first one being a 3. Event F says that they have to add up to 6. Okay, so that could look like, let's see, what would add up to 6? We could have a 1 and a 5, or we could have a 5 and a 1, because we are distinguishing between first and second die here, so it does matter which one comes up which. We could have a 2 and a 4, or a 4 and a 2, and we could have a 3 and a 3, and that's it. Those are the only options for getting their sums to equal 6. So what's E intersect F? What do these two sets have in common? Looks like the only thing they have in common is the 3-3 element. Okay, so I know what these sets look like. Let's find their probabilities. What's important when we're finding these probabilities is to remember again that there are 36 different outcomes if you're rolling 2 die. So the probability of E happening, out of the 36 possible outcomes, we wrote down 1, 2, 3, 4, 5, 6 that applied here. So a 1/6 probability for E. The probability of F, there are 1, 2, 3, 4, 5 out of 36. And the probability of E intersect F, there was only one element in that, so is 1 out of 36. So let's check. Does the independence formula check out? If these are independent, then the probability of that intersection is supposed to equal the probability of E multiplied by the probability of F. So does 1 out of 36 equal 1/6 times 5/6? Does 1 out of 36 equal, oh sorry, that's 5 out of 36. So does that equal 5 out of, what's 36 times 6? 216? Those two are not equal to each other. Those are not equal. So I would say these are not independent. They are dependent. And that should make logical sense if we go back and we really think about what's happening. Does the idea of the first die landing on 3 and the sum of them being on 6, like, do those affect each other? Well, sure, because if the first one lands on a 3, that kind of changes what the second one would have to be. So yes, these are definitely dependent on each other. If I know that the first one's a 3, that's going to change my mind about what the probability of getting a 6 sum is going to be. Okay, you could also get asked questions like this example. So it says if A and B are independent and the probability of A is 0.35 and the probability of B is 0.45, find both the probability of their intersection and the probability of their union. So since we know in this case we're given the information that they are independent, we can use this independent formula that the probability of the intersection should be the probability of A times the probability of B. So that would be, in this case, 0.35 times 0.45, which works out to 0.1575. And only after doing that can I find the probability of their union. So if they only ask you for the probability of the union, you are going to have to do that first step first anyway, even if they don't ask you for it. Because remember, the general formula for finding the probability of the union is taking the probability of A plus the probability of B and subtracting off the probability of the intersection. So if you don't have that intersection, then you can't complete this formula. So what is 0.35 plus 0.45 minus 0.1575? That should give you 0.6425. But what a lot of students don't do is they don't take the time to find that intersection probability first, and then since they don't have it written down, they totally forget about this last part of that formula that you have to remember to subtract off. Then finally, as a note here, be careful with your definitions. Independent and mutually exclusive mean very different things, but students get them confused constantly and they interchange them constantly, and they're not interchangeable. They don't mean the same thing. Independent events pertains to how the occurrence of one affects the other. Like, do they affect each other? Mutually exclusive pertains to the question of whether or not the events can occur at the same time. So I can certainly have events that can occur at the same time while they don't affect each other, okay? Or I could have events that do affect each other perhaps, but maybe there's no way for them to occur at the same time. So these are not the same thing. Be really careful about those definitions. It's just something that I see students struggle with a lot.